Okay, so we're going to start here. And this is good because I have just simple examples that I want you to think about. Okay, so we've got a set. It contains 3 elements, 1, 2, and 3. And so if I think about the number of objects, right, whoops, stop capitalizing for me. I've got 3, right? And now what if I want to do 2 permutations? So I'm setting R to be 2, right? This is what we've been working with. PNR, CNR, those combinations. Does anybody, just for fun, if I ask you for the 2 permutations, first of all, how many are there and what's the equation that I use? So I'm asking for, this is the notation that we come up with, right? So it's P32. How do I find that? So it's not n to the r, because I'm looking for the 2 permutations where I only allow, well, first we can list them. I want the ones that don't allow for repetition, right? So I could allow 1, 2, n 2, 1. I can allow 1, 3, n 3, 1. And I can allow 2, 3, n 3, 2. So we assume to begin with that we're not getting things like 1, 1, 1, 2. Yeah. So Samiksha, so you've got this. I see that you've got, so it's going to be n factorial divided by n minus r factorial. Okay, which is the same as 3 factorial over 1 factorial. So that's 3 minus 2 factorial. Yeah? Okay, but that's 3 times 2, which is 6. Well, okay, so did we get 6 elements? We've got 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, 3, 2. Now, I must admit, even though I listed it out that way because I wanted you to see permutations, so 1, 2, and all permutations of 1, 2, which is 2, 1, and 1, 3, and the permutations of 3, 1, and 2, 3. What's interesting about this, if you're trying to list out these elements, which I do ask you to do, and I know that's a bit of a tedious ask in problem 1, but the reason that I want you to do it is I want you to think about what you're getting. And here's a fun fact. If I asked you, and so I'll leave that there, but if I asked you for the 2 combinations of the same set, what would you give me? First of all, this is now I'm asking for CNR, which is equal to what? Okay, so I see we're getting answers there. So it's that n factorial divided by, I'm looking at, Samiksha has an answer real quick, that n minus r factorial times r factorial. I need to put another bracket there, something. So divided by all of that, right? And so in this case, as Samiksha has, that becomes that 3 factorial divided by 2 factorial, 1 factorial. So n minus r, and I clearly need parentheses. Okay. So as rightly stated, I see that somebody's got the answer of 3. So one of the things that's helpful when you're thinking about what that entails, so it's every subset that contains 2 elements, right? So we've got 1, 2, and 3, and we need to pick any 2 elements from that. And because it's a subset, that order doesn't matter. And so if I'm going to list those out, it's everything that could involve 1. So that's 1, 2, 1, 3. And then that's everything that could have all 2 element subsets containing 1. Okay, then I say, okay, well, I've done that. So now I want to think about all the 2 element subsets containing 2. Well, that's 2, 1, but I've already got that 1. And 2, 3. So I only have to look, if I put them in an order, and it's an artificial ordering, but I only have to look to the right as I go. So for 1, I have to match every possible combination that follows. So 1 and 2, 1 and 3. And then For 2, I only have to look to the right. So I have 2 and 3. That makes sense? Okay, what's important about that is if I come up here, sometimes it's hard to keep track of all the 2 permutations. That's a good mechanism for finding all the 2 combinations, but it's not a great mechanism for permutations because now it's every possible ordering as well. And so the easy way to do that is to find the combinations as we've done, and then find all permutations of that. 2, 1, 3, 1, 3, 2. And that gives you everything. So I do ask for the list, and so if you were to have a larger set, and I'm gonna come back up to this, which is why I want to say that. So let's say we have another set, A equals 1, 2, 3, 4. What that means is if I want the 2 combinations, so somebody list off the 2 combinations. First of all, how many are there? What's C4 to? Samiksha's method of just giving me the factorials is the best start. And make sure when you're doing your assignments, start with that. Because if you do go wrong, I know these are huge numbers, and somebody pointed this out. For assignment 7, what you'll note is some of your answers are very big. Now, I never went past I'm trying to think if I ever went past my scientific calculator. I don't think so, but I actually can hold a lot. And I also just dropped the powers of 10, which is an important point. I can just multiply by the powers of 10 later. Okay, so we've got a couple answers. But the point is, some of the things that I was asking about, they seem like simple things, like how many postal codes are there in Nova Scotia? How many postal codes in Halifax? The numbers that you got were immense, right? And I think, and part of this is understanding how these numbers expand so quickly, right? Postal codes on the whole, we have gobs of them across Canada. If you look at all the A9A, 9A9 combinations, there's a ton. But then when we restrict it, and you think to yourself, well, what restriction am I allocated to be big enough to accommodate the future needs of Nova Scotia? Is it okay to restrict ourselves to that leading B? You need to be thinking about what the scale of those things. So that E plus, yeah, so you had things that were to the power of 10. So generally on a calculator, if you see that, what you have is some number times 10 to a power. And some calculators show E and then a number, and what that's actually showing you is it's the number before it times 10 to the whatever follows the E. I see that, Luke. Okay, so I digress. So when we come back to this one and we start thinking, well, what does that look like here? So that becomes 4 factorial, as was stated, divided by 2 factorial, and then 4 minus 2 factorial, which is 2 factorial, or the at sign. Oh my goodness. Okay, so that's 4 times 3 divided by 2, or 2 times 3, which is 6. Which I think somebody already stated. And so the combinations then, as somebody mentioned, and this is what I was saying in terms of identifying those, I like to start with the first one listed in the set. And now sets are not ordered, right? But there's some ordering in the way that I present that. So if I'm trying to identify them all, I'm going to present them in order. So 1, all combinations including 1, 4, and then all combinations including 2. And for this, I only have to look to the right in the list at those combinations. So this might seem, so you're going to see why we're doing this in a second, because I'm going to ask you to expand all of this. And now I'm done with all the 2s, so I look at all the 3s. And that will be just the 1, 3, and 4. And 4 has nothing to the right of it to pair it with. Okay? All right. So then if I expand this and say, well, that's great, but I actually want the 2 permutations, hopefully you've got now a notion of what the number is, right? And that number in this case is P42, which is what? We know it starts with that. And then on the bottom, it's that 4 minus 2 factorial. Yeah, and somebody's already listed it, which is 2 factorial. I'm going to specifically write it out so that people remember that it's more than just that. So it's that 4 factorial, it's 4 times 3 equals 12. Okay, and it's twice of those. And in this case, because you're only looking at 2 numbers, there's only one possible permutation that we're missing. So you write that it's there's a multiplication by 2 to get to the number of 2 permutations. Because 1, 2, the permutations of that is 2, 1, 1, 3, 3, 1, 1, 4, 4, 1, and so on. Okay. But that need not be the case, because if I instead had asked you for the 3 combinations, what does that look like? And how many more of them are there? Now, I'm not going to list them out. I'm going to backtrack, and we're going to go back to some really simple examples and have you think about them differently. But this time, so exactly, Samiksha, you're just quick on the draw with these answers. I love it. So you've got 4 factorial divided by the product of 3 factorial and 1 factorial, which is just the 1. And so the answer there is smaller. And so sometimes people erroneously think when we're looking at bigger combinations, then we are going to get bigger sets. But of course, if I look at the 4 combination, you're right. So if I look at the 4 combination, how many 4 combinations are there? It's a bigger number. But the number of 4 combinations is the set itself, because what we're asking is how many possible subsets are there of a 4-element set that bring back a 4-element subset, and there's only the 1. And so this one's a little easier. It's 1, 2, 3, 1, 2, 4, and there's a reason I'm using this example. I'll show you in 1 second. And that's there's also 1, 3, 4, and then it's 2, 3, 4. Okay, and you could work through that. I think that's everything. And the reason that I wanted to show you this is if I then ask you for the 3 permutations, I said that a good way to find this, obviously we can do the calculation, and I will just for good measure. P43, 4 factorial, oh my goodness, there we go, divide by 3 factorial. Divide by 1 factorial, 4 minus 3 factorial. Helps to write it out. And that's 4 factorial divided by 1 factorial, which is then 4 times 3 times 2, right? 12, 24. Okay, as already answered. So in this case, it becomes useful to start from the combinations. If you were asked to find them all, 1, 3, 4, 2, 3, 4, we found the combinations. Combinations are easier to identify. Okay, so these are the starter combinations. The reason I say start here is now I can find all permutations of that 3-element set. That's easier than just saying find all the permutations. Find all the 3 permutations and list them out. That's hard. But finding the combinations, the subsets, it's an easier ask because you're finding a smaller set. You're only finding 4, right? And you have a system to handle that. So now if you want to find the permutations, now you're just looking at those three and you're saying, okay, what are the ways that I can reorder those? Well, if I leave the 1 in the front, I've already got one of those. The only other way is to flip the 2 and the 3. And then I say, okay, well, of that, I could put the 2 in the front. And then I always start from lowest to highest. That's just an approach I use. And then I have 2, 3, 1. What are the remaining 2? Do I have more? I mean, I know that I have 4 and I need to get to 24. And they're all permutations of these 4. So that means I have to find, for each of those possible rows, I need 6. Right? So I need 2 more. Yeah, so min, nice. 3, 1, 2 and 3, 2, 1. Okay, and we could go through and do this, but I would follow that same approach. So 1, 4, 2. And you see there's a pattern to what I'm doing. I'm going to then take the second element and then take the first and third. Oops, it helps if you take the right ones. And take the second element and then the other order. Okay, so you can keep doing this and you'd finally have that whole list. But this is an approach to finding them and making sure you have them. Now, what's my real approach? I would generate these in Intellij. I would write a JavaScript to create these combinations. That's the real approach. And there's no reason you shouldn't do that. If you're taking Java right now, you know how to do loops, you know how to create these things, you're welcome to use that. That's a valid and viable, completely useful tool. There's no reason that you shouldn't do that and just give us the output as the answer when I say list these things. Okay? All right, but you have to think about, well, what is that doing? And I'm going to step through some examples in Intellij in a little bit, but that's just to remind us where we came from when it comes to combinations and permutations. And now you see I went all the way back up. Okay, so here's my list of we'll start with permutations. That's okay. Okay, so what do you know about, and today is about you figuring it out. Okay, so let's start a little easier. Let's start really simple. Okay, let's have a new set. We'll go 0 and 1. Black and white. On and off, whatever you want. 0 and 1. 2 elements in the set. And if I asked you for 2 permutations, and I'm not going to ask this, you could figure it out, right? The number of 2 permutations of this are pretty straightforward because they have to involve the whole set. So it's 0 and 1 or 1 and 0. Yeah, exactly. The number, as was stated, is that P 2, which was 2 factorial over 0 factorial, which is 2. Because remember, 0 factorial is 1. Yeah, perfect. Okay, so those were 0 and 1. Okay, so how about, and this is why I said I'm going to start really simple. What if I said I want all the 2 permutations, but allowing repetition? So for instance, what's an example actually given my set? What am I asking for if I'm saying allowing repetition in this scenario? So that's correct, Mayank. It means that I'm allowing for 0, 0, and I'm allowing for 1, 1. But let's list them out. There's only a few, right? 0, 1 and 1, 0 are also in this list. Yeah, so items in the set can be used multiple times. And feel free today, it's like our last class, other than a review class, feel free to use your mic. We're not so scary. But what did I just list? What is this 2 permutations allowing repetition here? I've got my 4 elements. All the answers are absolutely correct. What do these look like to you? It's not the last class. We're going to cover a review of all the material in our last class. And then there's going to be a Q&A where you do problem solving in labs from now on. Yeah, exactly. Okay, great answer, Trent. So these are binary numbers. These are all 2-bit binary numbers. So anything involving these 2 digits in binary representation, I've listed them all. So when I talk about the 2 permutations of a 2-element set, I'm actually looking at the number of binary representations using that many digits or less. Okay, so this is that's one application. What are some other applications where we want to know what are the possible combinations, including or permutations that allow for repetition? Well, and what are some things that are not? First of all, what are some things that don't allow for repetition? That might be easier in real life. Yeah, feel free to turn on your mic. I see somebody did. Maybe. I got hopeful. Except we can't hear them. What if I had a set of I don't know, my son plays basketball. If I were picking a team to go to some tournament, is that with or without repetition? Yeah, without, right? I can't pick my son twice. Yeah, you can't pick the same number twice. Perfect, Sahir. So what are some other examples without repetition? The lucky draw, like in our example. Yeah, so if I have a set of tickets, right, and I'm going to do a lucky draw at a school, I give people buy tickets for a loonie, then what happens is when I draw the tickets, there's only one ticket. Now, what's an example of a lucky draw where you could be drawn twice? And there are examples of this out there. So, Samiksha, that's a great example. Grabbing a handful of Skittles. Yes, the handful of Skittles. Hopefully you don't put them back after eating it a bit. So these are great examples. But what if I were to say, okay, I've got these tickets, and typically I'm going to draw the number from the hat. I'm going to give you a prize. Okay. What if my prizes were of increasingly good value, right? So if I draw the first place first, if I take your ticket, you win. Well, you've already won the trip to Hawaii. Probably people would be very offended if I put your ticket back in. But if the first thing I drew was a pack of Post-it notes, you'd be pretty upset if I didn't put your name back in when you knew that the trip to Hawaii was coming. Yeah? So sometimes we allow repetition. And when it comes to sort of a lucky draw scenario, if I have these tickets and I'm putting the ticket back in the bucket to draw from, that means you could win twice. So you could win the pack of Post-it notes, and you could win the trip to Hawaii. Yeah, Luke. So Luke, is roll up the rim a repetition or not? Yeah, if we're talking about the possible, it depends on the way you look at it. I think if you look at it from the viewpoint of the person that could win, and I'm drawing a handful of potential winners, depending on your caffeine addiction, you could win more than once. I have been known to do so, but I've never won anything. 7, Luke. 7 $100 gift cards? Oh my gosh. I win like donuts. That is crazy, ridiculous luck. That is incredible. Okay, and where does he shop for coffee? Because I feel like I should be driving further for my coffee. Whoa, we have a neighbor that is renting a house who won the QE2 home lottery, won the home, and they've sold it recently, and they're looking for a place. Yeah, I would love any one of that group's luck. Okay, so this is so this is a different scenario, and obviously the counting mechanism with repetition is different. So now we've seen some examples of where we could apply this in terms of the real world when we're modeling things, but this is another example of where we would. It's an example that the counting is different. Right? When we look at 2 permutations without repetition, we see that there are 2. When we look at 2 permutations allowing repetition, there are 4. Okay, so let's go back and say, okay, so what does that give us then? What if I have, and we already used this example, what if I had this at 1, 2, 3? Well, we've already listed off the 2 we'll go with 2 permutations, or capitalize it, the normal 2 permutations, and we know that for this is 3, 2, and we already found out that that's 3 factorial divided by 1 factorial, which gave us 6, and we've already listed those out as 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. Okay, so what are the 2 permutations if I allow for repetition? What am I adding, I guess is the... Okay, and so make sure it has it. So we're going to have the same ones, but this time we're going to add in 1, 1, 2, 2, and 3, 3. So that seems fairly straightforward, but the real question is this. How many should I be expecting? What if I was looking at 3 permutations or of a 5 element set? What are the numbers that I'm getting? How do I know how many I'm going to get? So as in anything, what I'm doing is I'm counting the number of ways that I can place things into, I'm counting the number of ways that I can place elements into this specific ordering. And this is an ordered pair. So with permutations, that order matters. Okay, so we've got a few conjectures. We've got... So if I have n objects, well, let's take a look at how many we had. So, and then we'll check. So I have n objects, and I want an R permutation. So what are the conjectures that you could come up with based on the data that we have? So how many were there? First of all, up here, there were 4. And in this one, we added 3, so we started with 6, so then we ended up with 9. So we've got 4, 9. There's squares. That's a interesting start. 2 squared and 3 squared. Any other things that we could note? Do we need another data set? So the reality is when you're proving something, and honestly, as a computer scientist, you will be making conjectures like this where you're trying to figure out what the data is showing you. So you'll generate data. And typically I wouldn't just write out these permutations. I might write code to produce those. But then you would need to know the amount of those unique elements. So how would I come up with a conjecture for what this would look like? Maybe I'd run another example. Okay, so we see maybe it's n squared. Okay, and I think that's a valid conjecture. Is that, let's look at one more example, because if our running conjecture is n squared, so conjecture, the number of R permutations with repetition is n squared. Okay, yeah? What if we look at then, and this should be fairly straightforward because we already have an example, let's look at the 3 permutations of this set with repetition. How many of those do we think there will be? 1, 1, 1 is also allowed. And so now I can actually build this up in a different way. I can just build from small to big. So figure out for me, this is so what I'm demonstrating very effectively is the fact that it's really easy to miss things by doing this. And here's the point. Do I need to be doing it like this? What are my options? I don't work really well this way. I need a pattern for how I'm going to find things. What are my options for the first position? Just to make sure I have everything, what could I put in that first position? I could put a 1. I can fit a 2, or I can fit a 3, right? What can I put in the second position? Yeah, I can fit a 1, a 2, or a 3. And in the third position, I can fit a 1, a 2, or a 3. And I want all of those. So actually, what we learned from counting basics is enough. Right? I just have to pick all of those. So in fact, my Hank is right that all I have to do is look at, first I pick something for the first position, then I pick something for the second position, then I pick something for the third position, and it's all possible combination of that. Yeah, so 27. So there are 27 of which I'm missing some. And I could write a program to do this because I just want to put 1 to 3 in the first position, 1 to 3 in the second position, and 1 to 3 in the third position. So someone had already said 27, so 3 times 3 times 3. Yeah. Okay. So that doesn't look like 3 squared because 3 squared is 9. And actually what we should identify is the fact that if we thought that the number of 2 permutations on 3 elements is different than the number of 3 permutations on 3 elements, then this doesn't work. Okay? So then we've seen another couple. So this one is, nope, false. Okay, so then we come up with another conjecture, and I see, and we'll just take them in order. We see another conjecture, and that is that this is n to the n. Okay, so that works for this one. The number of 3 permutations is 27. And so that works. But unfortunately, the number of 2 permutations with repetition is on a set of 3 is not 27. Okay, so then I see, so this one's false. I didn't mean to already put a false on. Okay, so we'll take the false off. So then the final one is n to the r. And this is how you create conjectures in the real world, is you look at the evidence, you come up with an idea, and then you try to show it's either true or false, okay? And the question is, can we prove that's true? And the answer is yes. And it's really proof is simple. By the product rule, which we learned from counting basic, yeah, so that is our scientific method. We generate in this case, we're generating our own data, right? But then we're looking at that and we're trying to find, a rhyme or reason within the information that we have provided, we make a conjecture, and then we try to prove it. But we know that by the product rule, we can separate this into generating the number, into choosing the first element all the way up to that last element. And for each, we know that we have n options for that first one. We've got n options for the next one, n options for this, n options for the final one, all the way down to the last. Every time we have n objects that we're choosing from because we're allowing repetition. So we can choose anything in the set, and we know by the product rule that this is the same as n times n times n times n, and that's r times, which is the same as n to the r power. Your screen is freezing. Let me just, I'm not positive that I can help with that. I can certainly turn off. I don't know why I have these background effects on. I was in a meeting the other day. That might help a little bit, but I doubt it. Okay. I'm sorry about that. That's no fun. Brent, am I coming through okay on your side?
Yeah, it looks okay to me, yeah.
Okay. Oh, Luke, that's a bummer. I am recording this, so I will post that. Okay. And so that's not really a proof. Obviously, I'd have to put that out into wording. But essentially what we're saying is there are n ways to select an object, select an element from n objects. We do that r times. Okay, and by the product rule, that means our total number of times is having is n to the r. Found. Oh, I didn't realize we were having outages last night. I did get I won't be releasing the solution straight away. I did have a few people that did have outages and got in touch with me via cell phone, and I allowed for an extension. So just for the record, I'll be waiting 2 days to release the solution. But that's, anyway, just so you know, it's not me delaying. It's waiting until everybody's able to put that in. To that end, I'd ask that you not discuss the assignment with others right now until Friday. Okay? That'd be great. Okay, so let's then discuss what does that look like when it comes to combinations. I hope this is working out as a whiteboard. I'm very sorry about this. It's really frustrating to me to not be able to write. But I mean, our notes are captured, so that's a good thing. Okay, so let's work with the same set that we had before. Is this working out okay for everybody? So now we've got the combinations. And when we looked at, awesome, thanks Mayank for that feedback. So when we look at the combinations, and we looked at the two combinations, we've already done this, so I don't necessarily, but it's a good thing to like think to yourself, okay, what were they? They were pretty quick. It was that 1 2 1 3 2 3, and in combinations, remember, order doesn't matter. And so we know that there are C32, and that is 3 factorial divided by the 2 factorial, and then the 3 minus 2 factorial, which is 1 factorial. And so that just becomes 3. All right. What if we allow repetition? So what are the 2 combinations with repetition allowed? Yeah, so we only have to add in, 1 1, 2 2, and 3 3 in this case. Okay, that's cool. So let me introduce oops. How many do I want? 6. That's 6. I'll go like that. There. Okay. It's big. I want it smaller. Okay, so what if I was just looking at this and saying, you know what? What I want is the number of 1s, the number of 2s, and the number of 3s, right? How many of those am I counting? And I'm going to say, okay, this just drives me crazy. Center. All right. So in all of these combinations, we can only have 2 elements. So I just have to choose those elements a certain number of times. I'm allowed to have repetition. So I can choose to take 2 1s. But if I do, if I do, then I can't take anything else. Right? So this is how many times I'm going to capture something. Okay? No, that's a good point, Min. Do we need to take into account the null value in doing combinations and permutations? Good point. The answer is no. Yeah, Min is absolutely correct on this. So the empty set is a set, and it's called an empty set for a reason. Okay, so it is a subset of the set, but it is not an element in the set unless it explicitly is listed as an element in the set. So if you have a set of sets, then yes, you take it into account, but you don't take it into account when we're looking at my set 1, 2, and 3. Okay, so if I choose to take 1 into my combination, then I have to pick one of the other 2. So I could choose this one, but then I'm not allowed to take any 3s. Another option is to have a 1, no 2s, and a 3. Another option is to have no 1s and 2 2s and no 3s. I know this is getting super exciting to watch me write this out. 1 and 1, and I don't have to account for 2 with 1 because it's already accounted for. And then the only other option is that I have no 0s, no 1s, no 2s, and 2 3s. Okay, and what you'll notice in each of these rows, it has to sum to 2. Like if I look across the row, there's always, can only pick 2 in total. But it's looking at every possible way that I could do this. Okay, so what if instead, so I'm going to be a little silly, and I'm trying to get you to a proof of what that could look like. What if instead I represented picking one of those as something like this? So I'm going to get rid of the zeros. I'm going to say, I'm just going to represent the choice of an object as a star. So this is me choosing a 1 and a 2, and no, there. Here I'm gonna, whoops, cancel. No. I'm gonna choose a 1. I'm not gonna choose any 2s, and I'm going to choose a 3. So this is the same thing that I just had above, but instead I'm using, and it might sound silly, but you'll see where I'm going with this. So I'm just marking it as a star, just means that I chose one of those, right? So if I look across this row here, I'm going to hide that up above. What that means is, what does that subset look like? What is the combination that I'm looking at in that row that I've highlighted? Hopefully you can see the highlight there. What combination is that? Yeah, 1 3. So I have 1 1 and 1 3. 1, 3, or 3, 1. It doesn't matter because combinations, order doesn't matter. Okay, so now the only thing that changes, and this is where things get a little fun. I'm gonna go like this. The only thing that really decides this, I'm not gonna be able to do it quickly, is how many stars exist on either side of these borders. So if I put sort of a bigger border, oops, that's not what I wanted to do at all. Never mind. So if I were to draw this line very strongly, it's where that, so for instance, if I say the first one looks like this, star, line, line, I'm counting this boundary line right here and this boundary line right here. I thought I could draw. I just want to draw the borders. But at any rate, I never mess with this. So the first one looks like asterisk, asterisk, line, line, star, star, line, line. The question is, isn't this whole thing, can't I just consider this as a way of kind of where I place things? I've got 2 asterisks that I have to place. I've got 2 stars that I have to place. So the second row of this looks like a star under the 1, then a line, this line right here. Yeah. And then the next one, then I have a 2. So I have something in the 2, and then I've got that next line. Can you see this? So these are, anything on the outside of this is, I'm going to take away all the borders, and I'm just going to, I'll show you which lines I mean. So what I want to say is, it's where these lines exist. So in the first row, I've got 2 asterisks, and then I've got a line and nothing in between. In the second row, I've got asterisk, line, and this is a representation of what I have, right? If I were to say, well, what does this equal? Line, star, star, line. What is that equal to? What number is that? What combination is that? Yeah, 2, 2. Perfect. If I say, if I said instead, what is line, star? What number is that? Perfect. Okay, so what I want is a conjecture on the number of combinations. And what I know is for any of these, what I need to do is I have to place, so if I have n objects, and I have got r combinations that I want to make. So what does that equate to in terms of the number of stars and the number of lines? Which represents the objects themselves? Oh, actually, I'm sorry. How many stars am I going to have? Stars is the easy one. It might not be as simple as you think. So let's start with how many stars would I have? In this case, I have 2 stars, but if I want to find R combinations of n objects, how many? Yeah, so Trent, I have R stars. And how many lines do I have? In this case, I've got 3 objects that I'm choosing from, 1, 2, and 3. How many lines do I have? I have 1 between each one. So I've got 3 objects. At this point, I only have 2 lines. If I had 4 objects, how many lines would I have? I'd have 3, right? Because I'm just putting in the middle. So exactly what has been said is n minus 1. So I have R stars and n minus 1 lines. Well, I'm going to show you this because of time, because I want to go to Intellij. But essentially, the way that this works out is no matter what I do, I'm going to be placing R stars and n minus 1 lines. In my example, I'm placing 2 stars and 2 lines. Okay? And what that means is, in total, I'm choosing where to place in this location. And I'm going to choose to place R stars and n minus 1 lines. That means in total, the number, oops, here, we got to move it to the next place. So the total number of choices I have here, oops, the number of places that I can put things is a total of n minus 1 plus R. That's the number of places that I'm going to put these things, and I get to choose where I put the stars and where I put the lines, and I want every possible iteration, right? And so what that means is I need every combination of placement. So the conjecture, and there's a proof, and we're not going to go through the formal proof, but the conjecture that the number of R combinations of n objects, okay, is, and this is actually a theorem. We can call this theorem 2, and your original one, and I'll put this in your notes, that you came up with right here. It was a conjecture, but we proved it, so this will be theorem 1, was that the number of R permutations with repetition is n to the R. But our final theorem is that the number of R combinations of n objects with repetition allowed is the following. One of the two. It's Cn minus 1 plus R, comma R. So that's something we know how to calculate. It's also equal to the following. The number of n minus 1 plus R, and I'm going to demonstrate why in 1 second. You can take this as fact. Okay? So these are freebies, and I'll be posting this as a PDF. I might clean it up a little bit. But this is the number of R combinations, and the reason for that is as follows. If I look at that first thing, n minus 1 plus R, comma R, what we're saying, that's the same as saying that's the number of, this is based on the fact that there's a choice of where to place R stars, R asterisks. If you think about the combination n minus 1 plus R, n minus 1, this is motivated by the choice of where to place the n minus 1 bars. And you can think about the fact that they're equal because if you just assume that all the other positions, you only have 2 choices, right? So the number of ways that you could possibly put those bars is the same as the number of ways that you could possibly place those stars, because you're just going to fill in what's remaining with the stars or the asterisks depending on those iterations. So that's the motivation, but this is a theorem that you can just make use of, and I think it's only the last problem of the last assignment, assignment 8, that's already out, that you can make use of this, but that's that theory. Okay, so I know that's a kind of sketch of a proof, but hopefully it's enough to motivate where this comes from. So skip this. Let's move on to Intellij because it's more fun. Okay, so let's take a look at this. Here is an example, and I'm not saying which version I'm falling under, but I want you to take a look at what is happening. And if you dropped Java, or if you haven't taken Java, I I want you to think about what's happening. Anyway, okay, so I'll tell you what this does. So, here, for whoever found main and PSVM new to you, the other one is if you want to output, you can also type S out, system out, and just hit tab. Now I'm curious if print works, because I don't think so. That would be fun. But system out gives you the print line. Okay, and what I've asked of it is to output the result of print me when, let's start with an input of 3. So I want you to think about what that looks like. And this is, hopefully everybody's gotten to the point of getting to methods in Java, and I'm exploiting that fact. But it's okay, because really we're calling this one method permute me, and we are sending it a value of 3. Okay, so what I want you to think about is what's happening. So this method receives the 3, so that's what n is, okay? And it sets up an initial count equals 0, and then it says it's going to do, there's a series of 3 loops, so it's nested loops. For I equals 0 to I less than n, increase I. And then inside that, we say for j equals 0 to j less than n, increase j. And then inside that, and I know that within your classes, you've gotten to this point so far that you know nested loops. You've probably seen methods. I checked with your instructors there. So then we have another loop that's for k equals 0 to k less than n, increase k. So the question is, what's returned? What's printed in all of this? So if you're new to this, what happens is it runs I from 0 to n minus 1, j from 0 to n minus 1, k from 0 to n minus 1, and each time it increases the count. This is the same as count plus plus is the same as count equals count plus 1. Right. So what does this return? And which formula are we using? Are we using theorem 1, theorem 2, just PNR? So we see here, what is n in your scenario? Oh yeah, okay. So we sent it 3. So perfect. Actually, it's okay to give an example of this in terms of n, because I can change n and we can play with it. So take a conjecture in terms of n. So in this case, it's going to run. Yeah, Mayank, well spotted. So this is repetition. This is allowing for repetition because I is going from 0 to n minus 1, j is going from 0 to n minus 1, and so I, j, and k all hit 0, right? Good. This looks like permutation with repetition. Perfect. Okay, so what do I do then? Like, what is this going to output? We've got n cubed. That's our example, because our permutation with repetition is n to the r. And we're saying, okay, well, we're letting each of those positions encompass n objects, 0 to n minus 1. So in this example, we assume that what we're going to get is an output of 27, thank you, Luke, 3 cubed. So let's run it and see. Oh, I don't even, what? I just get rid of this. I don't even want to play with that. What did I do? Oh, I moved everything over. Silly me. Okay, so what happens if I spit it 10, if I give it 10 as an object? Anyone? which means I have faith. Okay, so I don't know if you can see it, but 27 is absolutely the right answer. So I want you to think about what that means, and all I have to do is change it here because I'm calling that method. So what if I give it 10 as input? Yeah, because our calculation, our conjecture that we prove to be true is that it's going to return n to the r, right? Which is n in this case is 10. We're going to let I, j, and k all be either 0 to 9, which is 10 separate options. So it's not that it's the numbers 1 to 10, it's that there are 10 objects that they can take into their position. And we're doing that 3 times, and so we get 10 cubed. So what happens if I wanted to represent, so that's an example of a permutation with repetition in code. And if I wanted to think about the number of steps that are taken by an algorithm, I have to understand that that's how I count that. Okay? And so some of this counting is just understanding, like when we start talking about efficiencies of programs and the number of steps that we're taking, this is why that matters. Okay, so let's we're at time. But if you were to modify this, and so I'm just going to cheat really quickly, because I have 1 minute left and I can do it, and I can stay, but that's not the point. You guys are busy people. If I wanted to find the number of combinations with repetition allowed, how would I do that? So I still am going to let that first one run through everything, but now I don't want to hit the same values that came before it. And so if you think about the ways that we used to do this, that we've done this before, is we don't want to, we look at what came before it, right? So what if I modified this? Is that what I want? I think this is not what I want. Well, I want you to think about, because I'm just mindful of the fact that we have 1 minute, which is not what I wanted to do. If I wanted to, I want to be equal to, if I do this, what would the count be? So now I'm allowing I to run from 0 to n minus 1, j to run from 0 to up to and including I, k to run from 0 up to and including j. Now what happens? What should the count be if I pass it? So I'm going to say, instead, I'm going to send to combine me. I'm going to send it, let's say 10. So we have an example of 10, should I do 2? Let's do 2. It's easier. Okay, so Mackenzie says we're going to get 1,000 with 10. I think, well, let's run 10. It takes 2 seconds to run it. Oops, sorry. Assuming. So, in fact, we get 220. And so what if I pass it 2? I get 4. Yeah, no. Oh, that was for 220 for combination. Thanks, Mackenzie. Sorry about that. Yeah, and so you can create code to do this. One of the fun pieces that you might wish to try is if you were trying to write out, like for instance, if you wanted to capture all these possible permutations and you started with a set, you can actually output them, right? If I output that triple, I now have all the possible permutations. If I output the triple here, I get all the possible combinations. So you can use this amazing tool called a computer to your aid, okay? And And you're free to use that on the assignment. And that's the big point that I'm trying to make. I used it to generate the possibilities for, well, all of it. But also, like when I was doing the check digit checks, I wrote a program to do that because it's just faster. And computers are very consistent. So they're going to not make the same mistakes that I will make on a daily basis. Okay, so that's it. That's the big last class. And next class, it'll be a review and we'll go over examples and it'll be it does seem easy. It's not so bad. It's just about applying it, knowing when to apply the right tool. Okay? All right, so I'll stick around, Brent. Good luck with everything.
Thanks. Yeah, I'll see you Friday.
Yeah, see you Friday.